We all know that the goal is to take humans to Mars in the coming years. Space agencies and companies are already developing their rockets and spacecraft to be able to do it. Thanks to SpaceX, it's becoming very popular to talk about the colonization of the Red Planet. All of this really started when Elon Musk, about 10 or 12 years ago, talked about creating a civilization outside of Earth. And now, this idea seems closer and closer, seeing the development that Starship is having, the spacecraft they have specially designed for that. Recently, numerous YouTube channels have emerged discussing space exploration. It's normal, as the topic is captivating and humans can achieve remarkable things when determined. But usually people focus on the topic of rockets. And I believe that the part of orbital mechanics which cannot be disregarded is often overlooked, and it's much more interesting than people think. The simplest and most efficient orbital maneuver that can be carried out is the Hoffman maneuver, known in English as the Hoffman maneuver. To understand it, let's give an example that takes place in real life, when we dock a capsule to the International Space Station. But due to movies like Star Wars or Star Trek, people think that moving through space is simply drawing a straight line, and this is not the case. What you really do is alter your parking orbit so that it intersects with the orbit of the International Space Station. This is how the Hoffman maneuver is performed to achieve the desired result. The process involves making a first fuel burn to convert the initial circular orbit into an elliptical orbit. By increasing the speed of our ship, what we do is increase the energy of our orbit, and that will cause the height to increase on the opposite side. The point where we have increased the speed becomes the perigee of the ellipse, and the opposite side becomes the apogee. It's important that you remember these names so as not to get confused during the video. Remember that perigee starts with P for proximate and apogee with A for away. This increase in speed is called delta 5 and is achieved when the rockets are ignited. Therefore, the greater the delta 5, the greater the fuel consumption we are making. The process involves igniting the engines, enough to get us into an elliptical orbit where the apogee just coincides with the orbit of the International Space Station. And when we get to that point, we'll have to reignite the engines to convert the elliptical orbit into a circular orbit that is exactly identical to that of the International Space Station. What you just saw is a textbook Hoffman maneuver. The most important thing about these maneuvers is that speed changes can only be made at the perigee or apogee of the ellipse. That's what a Hoffman maneuver is all about, although technically speed changes could be made at any other point in the elliptical orbit, but that would no longer be a Hoffman maneuver. And there you would be losing efficiency. When we talk about efficiency in orbital mechanics, what we really mean is consuming the least amount of fuel possible. The Hoffman maneuver I just described is the same process used when docking a spacecraft at the International Space Station. Because the most important thing is not that our spacecraft reaches the orbit of the International Space Station, but that it arrives just when the International Space Station is at that point, so they can dock. That's why our spacecraft in the first place will stay in a parking orbit around the Earth, waiting for the moment you have calculated that you should leave that orbit to coincide with the International Space Station. This is done taking into account the time it will take you to move from one orbit to the other. As we will see, taking this into account is crucial for going to Mars, and it actually determines the launch windows. If we go to an extreme case in which we greatly increase the speed we give to our ship, at perigee the apogee moves further and further away, until there comes a point when we will leave the gravitational influence of the Earth. That is, if we give it too much speed at perigee, we will leave the Earth's orbit. And this will no longer be an orbit, it will become a hyperbolic trajectory, like the typical ones in movies when making gravitational assists that approach a planet but do not fall into it. This happens because they carry too much speed, and instead of staying in orbit, they simply change their direction. Now, with this knowledge, we can comprehend the journey to Mars. First of all, we would take off from Earth and put our rocket into a parking orbit about 300 kilometers high. From there, we would wait until the ideal moment to make a fuel burn that would allow us to reach Mars. As I tell you, this thing about parking orbits is very common to wait until the ideal moment. The curious thing is that this time, we would have to leave the gravitational influence of the Earth, and to do this, as we just explained, we would have to convert our orbit into a hyperbolic trajectory. But really, if we zoomed out, we would see that despite having left the gravitational influence of the Earth, would we really now be in an orbit around the Sun? The process to know what is the perfect time to leave for Mars and coincide with it in its orbit around the Sun is very interesting. The reverse process is done on paper, assuming both coincide at the apogee during calculations. And the process is reversed in time until our ship reaches the moment of departure from Parkin's orbit. At that moment, one would have to look at where Mars is and a phase angle would be drawn. In this way, we would know that whenever this angle is formed, if we launched from Earth, we would coincide with Mars at the apogee of the orbit around the Sun. And this is the reason why there are launch windows, because we will be within the window whenever this angle is formed between Earth and Mars. The travel time is approximately 8 months, which is considerable, so you must bring enough food for the entire duration. Astronauts can't be compressed in a capsule like they were for the moon missions. The spacecraft isn't complete yet. But when the ship is approaching Mars, it will have to slow down again to exit the orbit around the Sun and stay orbiting the red planet. Once this fuel burn is done and it is already orbiting Mars, the astronauts could descend to the surface using a module, as was done in the Apollo missions. Could the whole ship descend like Starship plans to? Since it won't have modules that will detach and descend, but the entire ship will be the one that descends to the surface. But the reality is that Hoffman's maneuvers are not always the most profitable. There are other types of maneuvers that are sometimes more profitable than Hoffman's, but they are almost never used. Will you understand why? These are bi-elliptic maneuvers. The goal is the same, to change the orbit, but instead of doing it with 2 fuel burns, 3 are done. Let's give an example in which, for any reason, we would want to put a satellite in a circular orbit that was half the distance that the moon is. We are going to call this orbit Alpha Orbit, simply to simplify well then, doing a Hoffman maneuver. We would simply do a first fuel burn that would put the apogee in the Alpha Orbit. And once our ship reached that point, should we do another fuel burn to stay in that circular orbit? Well, the bi-elliptic consists of doing a first fuel burn, very strong, with the aim of putting the apogee of our transition orbit very far, much further than the orbit we want to go to. And once our ship reaches the apogee of that orbit, we would have to do a fuel burn to raise the perigee to the Alpha Orbit, and then, when we reach that perigee, we would have to do another fuel burn. But now in the opposite direction, that is, to slow down our ship, and in that way we would stay orbiting in the Alpha Orbit. Surprisingly, for this case and many others I just presented, it's more profitable. On paper, calculations show it's more profitable and consumes less fuel. The problem is that the flight time multiplies a lot. Initially, with a Hoffman maneuver, going to this Alpha Orbit would have lasted a day or a day and a half. When we apply a bi-elliptic maneuver, the travel time will have become between 20 and 30 days. That is, it will have multiplied by 15 or 20. And how much fuel are we saving with this increase in time? Well, in the best case scenario, you would save 6% of fuel. And as you can understand, it doesn't make sense to keep astronauts in space 20 times longer just to save 6% of fuel. Mainly because what you theoretically save on paper in kilograms of fuel, you really have to exchange for kilograms of food. For the astronauts in space, not only that, but all those extra days that the astronauts are in space, we would have to be monitoring the communications. There would be more days when something could go wrong, and in the end, as you can understand, it doesn't make sense. For extended missions, the spacecraft would need to be significantly larger than the cramped compartments used in the Apollo missions to accommodate the astronauts for longer durations. And for these reasons, really, for manned missions, it makes no sense to use a bi-elliptic maneuver. It is possible that for some unmanned mission, it could make sense. But I think the important thing at this point is to ask, where does that extra efficiency come from when we go so far, when we are applying a bi-elliptic maneuver? Couldn't something be done? Like, instead of going so far to save 6% of fuel, go a little further to save 1% of fuel? And that perhaps the trip would only increase by a couple of days. Could that be done? Well, the answer is no. To see it, we must look at a graph with the required delta 5 on the y-axis and the ratio of the target orbit radius to the initial orbit radius on the x-axis. If we are in a parking orbit 6,478.453 miles from Earth's center, when a 2 appears on the x-axis, it would mean that we would go to an orbit that had twice the radius. Well, now here we represent what the thing would be like. With a Hoffman maneuver, we would have something like this, but if we now did the same with a bi-elliptic maneuver, we would have this. where you can see that for ratios less than 10, the Hoffman is much more efficient, since to go to the same place it needs less delta 5. However, around 12 these lines cut, which implies that from this point it is already more efficient to use a bi-elliptic maneuver. Mathematically it works, but in real life other factors are more important, so it's rarely used. But be careful, because we have seen that bi-elliptic maneuvers have infinite combinations depending on how far you want to go. And that's why there will be a line for each of these options, so in reality there are infinite lines. In the best case scenario, it will only be profitable for you from 12, therefore you can't perform a bi-elliptic maneuver. To go a little bit further and make it more profitable for you, even if you increase the journey by a couple of days. To be truly profitable, you need to travel about 15 times the radius of the orbit you're departing from, which means going an extremely long distance. That's where the problems begin. Another important thing is, watch out, what's important in terms of when is it profitable to use a bi-elliptic compared to a Hoffman? It's not determined by how far you're going to go, but it's determined by the radius of the orbit you're going to divided by the radius of the orbit you're leaving. That's why going to Mars isn't even an option for the bi-elliptic trajectory. Because as you start from Earth's orbit around the Sun, the ratio to go to Mars's orbit is only 1/5 times greater. Even though the journey is long and we're going far away, we still haven't explained the source of the extra efficiency when using a bi-elliptic compared to a Hoffman. Well, this is because it's more efficient to increase speed when you're going very fast than when you're going very slow, like in the bi-elliptic maneuver. You make a very large initial fuel burn at the beginning when you're in low orbit. That's where that extra efficiency comes from. Because I remind you that when you're orbiting very low, the speed is greater than if you're orbiting higher up, and therefore when you make the first burn in low orbit, the speed was already very high. The reason for this is because energy goes with the square of the speed, and orbits are energy balances between kinetic energy and potential energy. Therefore, if you make a fuel burn when you're going very fast, as the speed goes to the square, you would be increasing the energy of the orbit more. Then if you made that same speed increase at the apogee, which is when you're going the slowest of the entire orbit. Another commonly used maneuver is the gravitational assist, which many are familiar with from movies. The idea is to pass close enough to a planet to be affected by its gravitational field, but to go too fast to stay in orbit. And that's why the planet is used to plot a hyperbolic trajectory. This allows us to use it to propel ourselves without spending fuel and reach places we couldn't reach. This method has been and will continue to be widely used for this reason. For example, in the Voyager, launched in 1977, that set out towards Saturn to perform a gravity assist maneuver, and later also do it in Jupiter. Voyager 2, also launched in 1977, accomplished a similar feat by passing Jupiter, Saturn, and Uranus. The cost to pay here is the time you lose going from one planet to another. But beware, because there is a misunderstanding with this gravitational assistance thing. The speed that we first gain when approaching the planet, we then lose it when moving away from it. The key is that the planets are not static, they rotate around the sun, therefore they carry a speed, and when we perform a gravitational assist, we are stealing part of that speed. So the speed that our ship is gaining, we are not gaining it thanks to accelerating as we pass near a planet, but we are gaining it by slowing down the planet in its orbit around the sun. And by Newton's third law, we would be accelerating. Here it is important to say one thing, and that is that in orbital mechanics it is assumed that changes in speed, that is, that delta 5 is instantaneous. When a rocket engine fires, the speed changes from one moment to the next, which does not reflect reality. What happens is that if we look at a trip that is going to last 1 or 2 weeks, firing a rocket for a minute is like an instantaneous change. That's why this theory is really good. But if we were talking about other types of engines, like for example ion propulsion engines, which are indeed on for a much longer time, this theory really doesn't work. Thanks everyone.